The next chapter is Spectroscopy A, Mass Spectrometry. Now, this chapter is part of a 3-chapter segment, and the chapters are Spectroscopy A, B, and C. Now, normally these come in between chapters 12 and 13 in your textbook, but I have grouped them together after chapter 13, and we're going to do these on one exam. So it'll be one unit of spectroscopy. So let's look, what is mass spectrometry? Well, it is a method for measuring how big a particular molecule is. What is its mass? So you can measure the molecular weight and determine the molecular formula of an organic compound. It's an extremely useful technique, and there's more than one type of mass spec, and we're going to talk about 2 of them in particular, but we will just keep in mind that there's more to it than what we're going over. So in a mass spectrometer, we take a molecule and we vaporize it so that it gets into the gas phase. Then we ionize it using a beam of high energy electrons. Those electrons have a lot of energy. And by a lot of energy, we mean about 6,400 kilojoules per mole for the electrons. If you want the electron volts, it's about 70 electron volts. This is just an enormous amount of energy to hit a molecule with. When an electron beam hits a molecule and it has this much energy, it causes that molecule to lose electrons. So you hit it with electrons and it'll cause it to lose some of its electrons. So that's what happens to the molecule. Once we've ionized that molecule, there's all kinds of things that we can do with that molecule. Mostly, we can send it down a long path and determine how big the molecule is. Now, the way that works is a little bit complicated, and as I mentioned, there's more than one way to do this, but this is sort of the basic schematic of a very simple mass spectrometer. So we start here with our sample where we inject it, and that injected sample gets heated up, and it goes through a plate to get us a fine beam, so not all of the sample goes into our instrument. And then we have an electron beam that hits it with high energy electrons that ionizes it. And then next we have an accelerating plate. That accelerating plate takes the charged particle, and because it's charged, it can move it with an electric field. And so it accelerates it to a very high speed. And then usually some sort of collimating plate. It's just a thin slit, so you get a very fine beam of particles. And then that beam of particles goes down a long path and through a magnetic field. Now, when a charged particle is moving through a magnetic field, that magnetic field will cause the charged particle to bend in its path. The amount that it bends depends on how large the particle is, how fast it's going, and the strength of this magnetic field. We'll find that the heavy particles do not bend as much, and the lighter particles bend more. By gradually adjusting either the magnetic field or the speed at which you accelerate the particles, you can time it so that different particles hit a small slit over here and a detector at different times, depending on how large the molecule is. And you can sweep through a range of masses and determine how much of each mass you had. It's really kind of remarkable, and it works really, really well. So let's look at a few details having to do with mass spec. What actually happens to the molecule when you hit it with the beam of electrons? Well, when that beam of electrons hits the molecule, it removes an electron. And we saw in the last chapter, anytime you remove an electron, you can create a radical. If that molecule didn't have any, if it had full octets on everything, and you remove one electron, that means something is not going to have a full octet. It'll have a lone electron, and so it will be a radical. And because if it was neutrally charged to begin with, it will become a cation. So we generate what is called a radical cation. And this is what's known as the molecular ion. Sometimes we can see that molecular ion and sometimes we can't. It just depends on how big it is, and it also depends on how stable it is. So the molecule, we hit it with a beam of electrons and we get a radical cation. Again, sometimes we can observe that radical cation with our mass spec, but sometimes that radical cation will break down into other particles, which include radicals and cations. And typically, the particles we see the most in the mass spec are the cations. The radicals by themselves, we cannot observe in the mass spec. It has to have a charge in order to work in a mass spectrometer. And I'll show you why. All right, yeah, so it has to be the cations that we measure. So let me show you why. All right, so it analyzes the mass of the cations. Here is the where the electron beam is. When that electron beam hits our molecule, and we generate the radical cation, cations can be accelerated by the electric field at this accelerating plate. If it's not a cation, if it's just a radical and there's no charge to it, it doesn't go anywhere. It doesn't accelerate down the tube. So we have to have a cation for this to work. All right. And then a mass spectrum is the information that we get plotted out on a graph. And this is what the graph looks like over here. We're going to blow that up in a minute and look at it in more detail. On the x-axis, we have the mass to charge ratio, so m is the mass, z is the charge of the particle. And then on the y-axis, we will have the relative abundance of each of those particles. Now, the relative abundance, I'll talk about that here and what that means. Most of the time when we do mass spectrometry, most of the particles have a +1 charge. And since they have a +1 charge, that means that the mass is going to be whatever the mass of the molecule is. So you're going to actually measure the mass of those individual particles. Now, there are some particles that do get a +2 charge, and so in that case, the mass would be divided by 2. But we're not going to observe those very often, and when we do, they're special cases, and we'll be able to know when that happens. But for all the ones we see in this chapter, we're just going to be looking at the ones that have +1 charge. So, understanding how a mass spectra works, or mass spectrum works. So again, it gives us the mass to charge ratio, m to z. That is on our x-axis, and our y-axis is the relative abundance. All right, and this is what we mentioned this last time, that since it's almost always +1, then the m over z measures the mass. So here's the interesting part. The tallest peak we're going to call the base peak. And the base peak is, again, it's the one that's there in the biggest abundance. It does not necessarily mean that that is the molecular ion. And in fact, I will show you some examples here in a little bit where the base peak is not the molecular ion, where the base peak is, 5 or 10 times bigger than the molecular ion. It all depends on the conditions that you use and also how stable that molecular ion is. All right, so here are some fragments. This is an example of a spectrum of CH4. Now, the mass of a methane molecule, CH4, comes out to 12 plus 4, so 16. And we'll see that our molecular ion is at 16. So that means that this is a radical cation at 16, and it flew, and it happens to be the base peak. It's the biggest peak in here. Well, some of those CH4 plus radicals are going to decompose to CH3 plus. And when they do, those also fly through, and that's going to have a mass of 15. So 12 plus the 3 hydrogens would be 15. We'll also observe some that are at 14. And so this one is at 14, there's 13, and there is 12. We don't observe any at 11 because carbon has a mass of 12. We can't have anything smaller than that. So we won't observe anything smaller. And you'll also notice that we have an M+1 peak, something as 17. Well, the reason that this happens is that about 1 out of every 100 carbon atoms in naturally occurring carbon is carbon-13. Carbon-13 is it's a naturally occurring isotope, and as I mentioned, it makes up about 1% of all the natural carbon. It's not radioactive. Carbon-14 is radioactive, but carbon-13 is completely stable. It just has an extra neutron in it. Well, that extra neutron means it's going to have a larger mass, and so we'll have an M+1 peak here at 17. And you'll see the abundance there is about 1.1%, give or take. All right, so what about those other peaks? Where did they come from? Well, I kind of alluded to that a minute ago. The molecular ion is often quite unstable, and sometimes you will observe it, and sometimes you will not observe it. And we'll often observe fragments instead of the whole molecular ion. If you want to get into a more complicated understanding of mass spec, you really have to understand the fragments. In this chapter, we're going to go for the basics. We are going to look at what is happening on a fundamental level and looking at molecular ions. But if you were to go further into mass spectrometry, you would be looking at this other stuff. But let's just look at the fragmentation pattern here for methane. Methane is pretty simple. You hit it with the beam of electrons. That beam of electrons causes it to lose an electron, and we get the radical cation CH4 plus, and then a radical. Now that decomposes pretty quickly, but enough of it sticks around that it will fly through the mass spectrometer, and we pick it up. It ended up being the base peak. But the other peaks that we observed are going to include the CH3 plus, which is that's the methyl carbocation, which this is one of the few ways you can actually observe that carbocation. You can lose another hydrogen atom, so hydrogen plus its electron, and you can get the CH2 plus radical. You can lose another hydrogen atom, get the CH, and then you can also observe just the carbon. All right, so you'll get 16, 15, 14, 13, and 12. And going back and looking at the picture just real quick, you'll see there's the 16, 15, 14, 13, and 12. And then we have that M+1 at 17. So we want to look at, again, just the molecular ion. We're going to go over to my document camera here, and we're going to look at these and determine what is the molecular ion for these substances. This is really easy. You're going to take the whole number that is typically associated with each of these. So for example, carbon, we'll do 3 times 12, gives us 36. Hydrogen, we'll do 6 times 1, gives us 6. And oxygen, 1 times 16, and that will give us 16. And when we add those numbers together, so 36 plus 6 plus 16, we get 58. So our molecular ion, M/Z, is going to be equal to 58. And that will be our molecular ion. So, like I said, pretty easy to do here. For this one, we'll do 10 times 12 carbons. And that gives us 120. And then 20 times 1, so 10 carbons times 12 is the mass, and then 20 hydrogens times the mass of the hydrogens, that gives us 20. And of course, that's going to give us 140. No need to put that in the calculator. So M/Z is equal to 140. All right, so now let's look at this one, C8H8O2. So 8 times 12. All right, we'll put that at 8 times 12, and that gives us 96. And then 8 times 1 gives us 8, and then 2 times 16 gives us 32. So we're going to add 8 and 32 to that 96, and we're going to get 136. So 136 M over Z is equal to 136. Perfect. All right. Now for this next one, something interesting happens when we do this one. It has a nitrogen in it, and so that causes an interesting pattern to occur. All right, so we'll do the 10 carbons. So 10 times 12 is 120. And then 15 times 1 gives us 15. And then nitrogen comes out to 14. So we'll do 1 times 14 is 14. And when we add those together, we're going to get 149. I'll go ahead and add them in there. So 120 plus 15 plus 14, and you'll see it comes out to 149. So M over Z is equal to 149. You'll notice when, and we'll talk about this in a little bit, but you'll notice when there is an odd number of electrons, you're going to end up with an odd M over Z molecular ion. So let's analyze a mass spectrum of a common organic solvent. It's used quite often, called hexane. All right, so hexane is C6H, what does that come out to? 14, C6H14. And if you add it up, the molecular ion should be 86. So C6, so 6 times 12 comes out to 72. And then if you add 14 more for the hydrogens, you'll get 86. And if we look over here, we can see the molecular ion is 86. All right. We do have a small M+1 peak. Again, it's about 1%. In this case, it may be a little bit more, but it's close to 1% of the size of our molecular ion at 87. So that makes sense. We'll find that the base peak, which is again the largest peak, and it is factored, it's scaled to 100 for whatever the base peak is, regardless of how much it is. If it's the biggest one, it's 100, and it is C4H9 plus, and it comes out to 57. I'll talk about these fragments here in a minute. You'll see every time it loses a carbon and some hydrogens, you'll get a little grouping of ions that show up, and we'll talk about those. So this is with 6 carbons, 5, 4, 3, 2 carbons. Again, we'll go over that here in just a moment. So we also have some major fragmentation peaks at 43 and at 29, and there's some smaller stuff that's around it. Again, we'll mention that here in just a minute. And then we have a minor fragmentation peak at 71, and that's this one that is right there. So let's try to figure out, let's look at what we call the nitrogen rule, and then we're going to come back and look at hexane and look at its fragmentation pattern. So compounds that only have carbon, hydrogen, and oxygen are always going to have a molecular ion with an even mass. All right. We have what's called the nitrogen rule. And if you go back and look at our rules in chapter 10, I believe, when we talked about calculating degrees of unsaturation. Well, remember when we were calculating the degrees of unsaturation, the actual number that we put in there, which wasn't necessarily the actual number, is if there was a nitrogen, then the actual number was going to be an odd number. And so because we had to add 1 for each nitrogen. Well, that's just because nitrogen is it is trivalent instead of tetravalent, and it ends up giving us odd numbers when we have odd numbers of nitrogen. So here is an example. We look over here. This is some. I always seem to be showing you drugs, but here this one is 3-methylfentanyl, which is a very powerful opiate. And this particular one has 2 nitrogens, and because it has 2 nitrogens, it has an even molecular weight. This one, the MPPP, which is the 1-methyl-4-phenyl-4-propienoxypiperidine. That's a lovely name. It has a molecular weight of 247, and the reason that it's odd is because of that nitrogen. And test this for yourself. Go look at a few compounds that have one nitrogen in them, and if they are neutral compounds, you will see they are going to have an odd atomic molar mass. So let's look at number 2 on our in-class assignment. Switch back again over to our document camera. Here, I'll do this. All right. We want to propose 2 molecular formulas for each of the following molecular ions. Now, there's more than one possibility that can go with each of these. And the thing I recommend doing is, if it's an even number, just take that number and divide by 12, which is the mass of carbon, and see what you get. So 72 divided by 12, of course, is going to come out to 6. So I suppose we could have a molecule that is C6, but it doesn't have any hydrogens. That, I do not know of a C6 molecule. There probably is one out there in existence somewhere, but it's most likely that we're not going to have 6 carbons. We will have 5 carbons. So I'll put C5. So let's take C5. So 12 times 5 gives us 60. And let's subtract that 60 from 72. And that gives us 12 hydrogens. Well, that makes sense. Carbon, when you have like a pentane and it's fully saturated, it would have 12 hydrogens. So this particular molecule, pentane, or that formula for pentane, would have a mass of 72. All right. Now, we're probably not going to be able to fit a heteroatom in there like nitrogen or oxygen. Well, nitrogen, since it's even, we'd have to have an even number of nitrogens. And oxygen has a mass of 16, so that wouldn't work. So let's go down to C4. All right, so 4 times 12 is 48. We'll do 72 minus 48. And that gives us 24. Well, we can't put 24 hydrogens on 4 carbons. That's just not going to work. But we could put an oxygen in there, and oxygen is 16. So I'm going to subtract 16 from this, so minus 16, and that gives us 8. So we could have a molecule C4H8. Let me fix that real quick. So C4H8O. And again, so that'd be 48 plus 8 would give us 56. Plus 16 would give us 72. So that would definitely work. And I don't know of any other 4 carbon things that would work because there's just not much options left there. Let's see. I suppose we could do a fluorine, but then we're getting down to a ridiculously small number of hydrogens. 3. Well, yeah, we'll just ignore that. All right, so now let's look at the possibility of C3. All right, so 3 times 12 is 36. We're going to subtract that, so 72 minus 36. That means we have 36 left to work with. If we did 1 oxygen, we would have 20 hydrogens. That's probably not going to work. Let's do 2 oxygens, so we'll do O2. And we'll subtract 32 from that 36. So 36 minus 32. And that gives us 4. So we could have C3H4O2. And I can think of a molecule that has that formula. Here, I can sketch it over here, what that would look like. We could have... So 1, 2, 3, 4 hydrogens, 1, 2, 3 carbons, and 2 oxygens. All right, so and this is just called acrylic acid. All right, so that is just an example of what that could be. So those are a few possibilities. Let's look at this one. So we'll do 100. So let's do 100, and we're going to divide by 12, which is the mass of carbon, and that gives us 8.3. So the most carbons we can possibly have in this would be 8. All right, so let's see what we have left when we do. So 8 times 12 gives us 96, and we'll subtract that 96 from 100. So 100 minus 96. I didn't need to do that. That's 4, obviously. All right, and so we would have H4. Now, I don't know of any stable molecules that have that formula, but it's a possibility. I wouldn't put this high on our list. If we have an unknown with a mass of 100, that's not going to be my top suspect there. So let's go down to 7 carbon. So C7. All right, so 7 times 2 gives us 7 times 12. Let's try that again. So 7 times 12 gives us 84. And then let's subtract the 84 from 100. That's going to give us 16. So H16. All right. Well, that is a saturated hydrocarbon. That would be like heptane, and that would definitely work. All right. Let's look at another possibility. Let's look at C6. All right, with C6, we're probably going to need at least an oxygen, but let's do 6 times 12 gives us 72. We'll subtract that from 100, so that gives us 28. So there's 28 left. So it can't all be hydrogens, but if we put an oxygen in there, so let's subtract 1 oxygen from that, and we'll get 12. So C6H12, I did that again. C6H12O, and that would definitely work. So again, that would be 72 plus 12 is 84, plus another plus 16 would give us 100. And I suppose we could go down to 5. So C5, we probably need 2 oxygens here. So 5 times 12 gives us 60. That means we have 40 left. And so we'll do 40 minus, let's do 2 oxygens, 32. That gives us 8. So C5H8O2. And I could definitely think of a lot of examples of things that have that particular formula. I don't know if it'd be a ton of examples, but I could definitely think of some examples. All right. Let's see, what would the degree of unsaturation? So 12, it have a degree of unsaturation of what, 2? Yeah, that's definitely something that's doable. All right, on this one, scoot that over a little bit. On this one, we've got an odd number, which means that we have at least 1 nitrogen. So let's go with the possibility of 1 nitrogen. So we'll put the N over here. We'll do 73, and we'll subtract 14 from that, and that gives us 59. So let's take that 59 and divide by 12, and that gives us 4.9. So we'll do C4, and then 1 nitrogen. All right, so 59 minus 4 times 12 is 48, and that gives us 11 hydrogens. So C4H11N. And remember, you can have an extra hydrogen in there because of the nitrogen, and this would be like butylamine would have that formula. So that would be an example. All right. The only other possibility is if we had 3 nitrogens. Remember, if there's 2 nitrogens, it's going to be an even number. So 3 nitrogens. So 14 times 3 gives us 42. We'll subtract 42 from 73. So 73 minus 42 gives us 31. And so that's going to give us a maximum of 2 carbons, right? If we divide that by 12, we have 2. So we'll put C2, and then we'll do that 31 minus 24, and that tells us we have 7 hydrogens. Now, offhand, I don't know of a particular molecule that has this particular formula. The one up top is much more likely than this one, but it is a possibility. All right, so I want you to be able to determine some possibilities, at least one possibility for a given molecular ion, And I also want you to know that odd number rule about nitrogen. So let's switch back over. All right, switch back over, and we're going to look at alkyl halides. So alkyl halides do something kind of interesting because of the isotopic abundances of some of the alkyl halides. We'll start with chlorine. Chlorine, as you may or may not remember, we're going to look at a periodic table here. So let me switch back over to our document camera. So there's chlorine at 35.45. Now, when scientists were first trying to devise a periodic table and they were trying to figure out what, the masses of things were, this gave them all kinds of headaches. That it's 35.45. It's halfway in between, almost halfway in between 35 and 36. And they couldn't figure out why that was because they didn't know about neutrons. They didn't know about isotopes. We know about isotopes, and we know that chlorine is made up of two isotopes. And those two isotopes are Cl35 and Cl37. And that the ratio, the naturally occurring ratio for that is about 3 to 1. It's like 74 to 26 or something like that. It's maybe 76-24. But anyway, it's very close to 3 to 1. That means that when you observe the molecular ion, you will observe a peak that's the molecular ion, and you'll see one that is +2 bigger, and it's about a 3 to 1 ratio. And that is a giveaway that you probably have a chlorine. All right, so you'll have compounds that with a chlorine atom that's an M+2 peak, and it's going to be about 1/3 the size of the molecule. And you'll see this in all of those compounds. If you look at the fragmentation, there's some interesting fragmentation that occurs. Here you end up losing a methyl group to get this fragment. And then this fragment is where you actually lose, this fragment's where you lose the chlorine atom, and you end up with a carbocation. All right, but we're primarily interested in that molecular ion and the M+2 that's about 1/3 its size. That's a dead giveaway that it's chlorine. Well, bromides do something similar, but we're going to look back over here. So here's bromine, right? It's at 79.90. That's really close to 80. And if you were to just guess how many bromine atoms are bromine 80, well, the answer to that is hardly any. And the reason for that is that bromine 80 is not a stable isotope. It undergoes beta decay and gives you something else. I guess it gives you, it would give you the krypton. All right. So bromine, you get bromine 79 and bromine 81. And they're almost in a 50-50 ratio. There's a little bit more. There's a little bit more of the bromine 79 than there is of the bromine 81, and that's why it's a little bit less than 80. So bromine has two stable isotopes. Again, they're 79 and 81, but it's almost a perfect 1-to-1 ratio. That means when you observe the molecular ion, you will have a molecular ion that is almost 2 equal sized peaks, where the first peak is just a smidge taller than that second peak. All right, so you'll have a molecular ion and an M+2 peak that is approximately the same size. All right, so we want to look at what molecular ions we should expect here for these, and including any significant isotopic peaks. All right, so let's do the C4H9Cl. All right, so 4 times 12 will give us the carbons, and then we'll do 9 hydrogens, and then we'll do 35 for the chlorine. Remember, we're not going to do 35.45. We're just going to do 35. So 35 for the chlorine. And that's going to give us a molecular ion of 92. So C4H935Cl is going to have an M over Z that is equal to 92. And if it were C4H937Cl, it's going to be 2 bigger. So you'll have one that's at 94, and you should expect this to be in a 3-to-1 ratio. And so that's what the peak pattern would look like for that. Fluorine, you'll notice I didn't mention fluorine in the presentation, and the reason I didn't mention it is that there's only one stable isotope of fluorine, and that is fluorine 19. So we can just stick with 19 for that. All right, so we'll do 3 times 12 plus 7 for the hydrogens, and then plus 19 for that, and that's going to give us our molecular ion at 62, and that's our M over Z, and that should just be a single peak, and we're ignoring the M plus 1 peak that's about 1%. We're just paying attention to major peak patterns. All right, here is this one is for bromine. So bromine, we have 79 and 81. We're going to go with 79, so we'll do 6 times 12 plus the 11 that are there plus 79. And that gives us 162. So the C6H1179Br is going to be 162. And if we look at C6H1181Br, that's going to be 164. And that this should be approximately a 1-to-1 ratio. Remember, for bromine, it is 1-to-1. We'll go back and look right here. There's that 1-to-1 ratio. All right, sorry, I hit my microphone there. All right, next, let's look at this one, the C4H11N. This should be an odd number because it has 1 nitrogen in it. So 4 times 12, that's 48, plus 11, that gives us 59, plus nitrogen is 14, and so that's going to give us 73. So this one should have 73, and it should be a single peak. We shouldn't have an M plus 2 peak on that. All right, for this nitrogen, because there's 2 of them, we should observe an even number. And so let's do that. So 4 times 12 plus 4 plus 2 times 14. And we'll put that all together and we'll get 80. All right, and that also will be a single peak. All right. So we're going to look briefly at fragmentation patterns. I am not going to test you on complicated fragmentation patterns, but it is something worth understanding why it happens and what's going on, because it can help you get a little bit more information about your molecule and why you're seeing the particular peaks that you are. So the molecular ion is the thing that like 90% of chemists look at. That's what they care about. But those fragmentation patterns can be quite significant. So we'll find that different functional groups will have different kinds of fragmentation patterns. So going back to hexane that we saw a little bit earlier, when you lose the methyl group at the end, well, methyl is a carbon, which is 12, and 3 hydrogens, which are 1 each. So that gives you a fragment that's about 15. So when you lose that, your ion is going to be about 15 units less than your molecular ion. And so our molecular ion for hexane was 86, but we did have, it was a minor peak, but we did have a peak at 71. That was where we lost 1 methyl. So let's go back and look at let's go back and look at the spectrum in hexane. So here's our molecular ion, which was 86. All right, it's out there, and it's not the base peak, but it is a significant peak. When we lose, every time every time we start cleaving off these carbon-carbon bonds, it's going to drop by, either 12, 13, 14, 15. It just depends on where we're starting. But here we have one that's at 86. If we lose 15, we get to 81. So that's where we've lost the methyl group from the end. If we lose a CH2 from that, we'll lose 12 plus 2, that'll lose 14, and that will get us to 57, which is our base peak. All right, and if we lose another CH2, we'll lose another 14, that will get us to 43. And then if we lose yet again another CH2, that'll get us to 29. And so that explains all of those peaks. The smaller peaks are where we've lost hydrogens in addition to losing a carbon. So that explains why we observe what we observe. So it's a pretty cool thing. Now, for compounds that have functional groups, the fragmentation patterns are a little bit predictable. All right, so aldehydes and ketones, you'll often get what's called alpha cleavage, where you cleave the bond between the carbonyl and the alpha carbon. All right, so you'll break that bond between the carbonyl and the alpha carbon. The alpha carbon is just the adjacent carbon to the carbonyl. And when you do, you form something that is a resonance stabilized acylium ion. So you get this CO, and it's got a plus charge on the carbonyl, on the carbon, and you can draw the resonance structure with the plus charges on the oxygen. Since it's resonance stabilized, this will stick around a little bit longer than other things. And so we should be able to observe that when we have a carbonyl compound. All right. For alcohols, we get something very similar that occurs. Again, we cleave at the alpha location. We cleave in between the carbon that has the oxygen on it and the carbon that is adjacent. So again, you get alpha cleavage. All right, I fixed something there that should have said alpha cleavage. So you'll get alpha cleavage there, and you get a resonance stabilized carbocation. This is one that we'll see quite a bit over the course of this semester. And it's possible that this can undergo or the alcohol can undergo a different kind of dehydration, or a different kind of reaction where it does dehydration, and you get an alkene. So it's not uncommon to see these kinds of fragmentation patterns. All right. For amines, you get something that's very similar to what happens with alcohols. You get the alpha cleavage. All right, the alpha cleavage. We get a breaking of the carbon with the nitrogen and the alpha carbon, and when that happens, we get this resonance stabilized carbocation. Something else that can occur is that you can get instead of an alpha cleavage, you can break here at this between the alpha and the beta, and you can form another resonance stabilized carbocation. So there's several different ions that can form. So it's essentially you're losing a methyl group there. All right, our final two things. One, we're going to look at high res mass spec, and then we will look at GC mass spec just ever so briefly. So everything that we've looked at up to this point has been low resolution mass spectrometry. And that's where we have resolution on our mass spectrometer to the nearest whole number. So, we can detect, one that's at 80 and 81 and 82, but we couldn't get like 81 and a half. Well, it turns out that there are mass spectrometers out there that can do what's called high resolution mass spectrometry. And it can get that M to Z ratio out to more digits. It can go out to 4 digits, which is a common one that's used for organic high res. although there are some that go out to like 6 or 7 digits. And so here's the thing. These high-res mass specs, they cost a lot more money than just the regular mass spec. Typical low-resolution mass spectrometer, you can get somewhere in the, you know, $10,000 or $20,000, which I know that sounds like a lot. You know, you could like buy a whole car with that or something. But the high-res mass specs, the one that go out to about 4 decimal places, they typically are going to run in the several hundred thousand, so 10 or 20 times more than a low-res mass spec. So they're a lot more expensive. So the reason that we like high-res mass spec is that it helps us to distinguish the very subtle differences, right? A lot of our atoms aren't exactly whole numbers, right? Like carbon, by definition, it's 12. But for example, hydrogen, at a mass of 1.00783, it's not exactly 1, right? For oxygen 16, it's not exactly 16, all right? It's 15.9949. Nitrogen is not exactly 14. Well, we can measure those very small differences using a high-res mass spec. All right, so think about this. Let's say we have a compound that has a molecular ion in a low-res mass spectrometer of 60. Well, there are several compounds that we can look at that have a mass of about 60. All of these would show up at 60 on a low-res mass spectrometer. However, in a high-resolution mass spectrometer, we can differentiate between these. And we would be able to tell which one of these we had, or at least we would have a better idea of which one we had. There's a little bit of error when you're doing these, and we'll see that when we do number 25. All right, so let's go over our in-class. We'll clear that. All right, so a low-res mass spec showed an unknown neurotransmitter had a molecular ion of 153. So 153. There are a couple of possibilities that have been proposed, C8H11NO2 and C7H11N3O. We don't know which one is the right answer. So when we do a high-res mass spec, it gave an exact mass, we should put that in quotes, exact mass of 153.068. All right, what is the molecular formula? And the way that we answer this is that we calculate the high res for this and for this. So we've got 3 carbons, or not 3 carbons. We've got what is this? 8 carbons. So we'll do 8 times 12.0000, and I'm going to go back here. And we're going to use these numbers here. All right, so 12.0000. All right, for the hydrogen, we've got 11 of those. So 11 times 1 point, and again, let's go back, 0.00783. All right. And then for nitrogen, we've got 1 times 14.0031. And then for oxygen, we've got 2 of them, so 2 times 15.9949. All right, so let's put all these numbers in. So 8 times 12 comes out to 96. Probably didn't need a calculator for that one. 96.0000 on that one. So for the hydrogens, we'll do 11 times 1.00783, and that gives us 11.08613. All right. Let's do the nitrogen. Well, we don't need to put that in. It's 14. 1 times any number is itself. So 14.0031. And then we'll do this one. 2 times 15.9949. And that gives us 31.9898. And now we can add these together. And so I'm just going to add them together. So 31.9898 plus the 14.0031 plus 11.08613 plus 96.000. And the number that we get here, and we're just going to go out to the fourth decimal point, so 153.0790. All right, and so we'll see that's pretty close. That may be it. The numbers here are often not perfect, and that's because the calibration isn't always exact. Usually the calibration it's usually within about I don't know, 15 or 20 parts per million. So let's go and look at this other one. So we'll do 7 times 12.0000, 11 times 1.00783. We've already got that number. Nitrogen, we've got 3 of those, so 3 times 14.0031. And then finally, 1 oxygen, 1 times 15.9949. All right, so 7 times 12 is 84, so 84.0000. Make sure that's staying on the page, all right, on the screen. And then the 11, we did 11 here, so I'm going to just write down that same number, 11.08613. And then for 3, so 3 times 14.0031. As you can see, I'm putting in the right numbers there. And that gives us 42.0093. And then finally, we'll do 15.9949 for that one. And now we can add these together. So I'm going to just clear all that out. We'll put 84 plus 11.08613 plus 42.0093 plus 15.9949. And that gives us, so 153.0903. And if we compare this one and this one to that, this one is closer. And so we're going to say that this is our correct number, which means the C8H11NO2 is going to be the correct formula. All right, well, that's all for the in-class assignment for this chapter, but we do want to go back and look at a couple of things before we close out the whole chapter here. All right, we already talked about that. So there's a thing that's called gas chromatography mass spectrometry. And gas chromatography, we've talked about gas chromatography in our lab. And in gas chromatography, you can separate your chemicals out using a gas chromatograph, where you inject the sample in, and it uses how much the compounds adhere to the inside of this column. Some compounds will stick more, and other compounds will stick less. And so it separates them out, and you can detect them at different times. And so we've seen stuff like this in the lab where we'll have different peaks. So we inject the sample. This one looks like it has 3 main things and maybe something else out here. So you can take each of those individual ones, because you don't need a whole lot of material for mass spectrometry. You can take those small amounts and send them through a mass spec. and you can generate peaks for each of your peaks. So you can generate a mass spec for each one of these gas chromatography peaks, which that's really cool. So even though you have a mixture of things, you can get an idea of what it is. You can even take this and do high-res mass spectrometry with it if you're very clever, although that costs a lot more to do. But this is just an example of what you can do. So if you've got a sample of compounds, you can kind of determine what they are and then combine that with some of our other spectroscopic techniques that we're going to talk about in future chapters. You can get a pretty good idea of what these compounds are, even if you have quantities that are so small, you may not be able to isolate them very easily. So one thing that GC mass spec is used for is for drug testing. There are certain jobs where people just cannot do drugs at all. Certain jobs that involve using heavy equipment, or if you have to have a criminal background check, you can't run off to Colorado and go get yourself some edibles. So some employers will take this very seriously, and they will make sure that you are not consuming cannabis. And so one of the compounds that is a principal psychoactive component of marijuana, it's the THC. And THC here is the structure of THC. And if you look, has a molecular ion of 314. So it's possible that you could take a sample of somebody's urine, and if there's some of this THC or one of the metabolites of it, then you could extract that from the urine, purify it, concentrate it, inject it into the mass spec, and get an idea. And if you really think it's that, then you can double check it with the high res mass spec. But it gives that peak at 314, and that is its molecular ion. Now, this alone may not be enough to prove that somebody was doping, but they use similar techniques to this to determine if people are using these kinds of drugs. And of course, like with the Olympics, they look for other kinds of things having to do with steroids and other performance enhancing things. But this is a very common technique, and it also is used extensively for quality control. For example, if you've got a distillery, and you're distilling an alcohol, you could take the alcohol and inject it and see what other compounds are in that alcohol, and that will help them to determine if their product meets quality control standards. All right, well, that is the end of Spectroscopy A. And the next one coming up is Spectroscopy B, and it's going to be on infrared spectrometry or spectroscopy.